Hey everyone, it's Dr. Walker. Let's go over the third example from video 53C on finding the center of mass. In this problem, we want to find the center of mass of a uniform semicircular arc of mass m and radius r. So instead of having a rod of length L like we did in the previous problem, we now have an arc. It makes half of a circle. The first thing when doing any of these types of problems, the first thing to do is think about, is there any symmetry in this problem? Because this can help us find some of the coordinates for the center of mass. First of all, this half ring here is on the xy plane, so we know that the z coordinate of the center of mass is going to be 0. What about the x coordinate of the center of mass? Well, if we look at the x coordinate, we see that we have half of the mass along the negative x and half of the mass along the positive x. So we know that the mass is evenly distributed along the x-axis, so the center of mass location, the x-coordinate, will also be 0. So when we're finding the center of mass of this half ring, we only need to look at the y-coordinate. Let's write down our expression to find the y-coordinate of the center of mass. 1 over m integral y dm. So in the previous problem, when we had the straight rod, we broke it up into a bunch of little dm's here, and they each had a length dx. But now we want to do it a little bit differently because this is a circular object. What we're going to do is we're going to take a little piece here, call it dm. This is going to be our little dm. But instead of saying it has a length dx, we're going to say that the length is going to be dl. Let me give you a tiny bit of background information that is very useful for problems that are circular instead of straight. Consider a circle. Remember the old unit circle? Consider an arc on this circle. We can define an angle theta. And we say this angle subtends this arc. When this angle theta is measured in radians, we have the definition that theta equals the length of the arc, we can call it L, over the radius. We can call it capital R. The radius, it's a circle, it all has the same radius. This definition should make sense to you because if you think about the full circle, the angle theta would be 2 pi. The length of the arc would now be the full circle, which is the circumference of a circle, which is 2 pi r. If you divide by r, you can see indeed that this equation makes sense. So that's a little bit of background information. Now that we have this, we realize, well, L is equal to r theta. Now we can come up with an expression for dl. Well, the only difference between L and dl is that dl is really, really small, and instead of being subtended by an angle theta, it's going to be subtended by a very, very small angle. This very small angle here is going to be called d theta. So now we have an expression for dl equals r d theta. That's going to be useful. We're almost there. Remember when we did this problem over here, we said dm was equal to lambda dx. What do you think dm is going to equal to this time? Instead of using dx, we're going to use dl. Right? The length of our little mass element dm here, the length is dl. So for dm, we can put lambda dl. And now we can use our substitution. For dl, we can put r d theta. We know that we're going to want to integrate this little mass element from 0 all the way to pi. But before we do that, we have to get rid of y here. We can't have a Cartesian coordinate system mixed with our polar coordinates. How can we write y in terms of theta? Well, if you think about the location of this point here, the coordinates, right, x, y, use a different color here. If you think about the position y here, you make that triangle. This big angle here is theta. Right, because we're integrating theta from 0 all the way to pi. So the y-coordinate is opposite theta, which is r sine theta. common substitution that we use to find the y component here. So we're going to have 1 over m integral of r sine theta lambda r d theta. Now we notice that we have a lot of constants, r, lambda. Lambda is a constant because the rod is uniform, and r. We can take the constants out. We're going to have r squared lambda over m. Then we're going to integrate sine theta d theta from 0 to pi. The integral of sine theta is negative cosine theta. So we're going to have r squared lambda over m negative cosine theta from 0 to pi. When we plug in pi in here, in negative cosine of pi, we're going to get 1. So let me just put little parentheses here. So we're going to have 1. When we put in 0, we're going to get negative 1. So 1 minus a negative 1 is what we're going to have. We're going to get a factor of 2 from this integral. We're going to have 2 r squared lambda over m. So you may be thinking, are we done yet? Well, we only want our answer in terms of the variables that are given in this problem, which are m and r. So we need to rewrite lambda in terms of that. Remember our definition of lambda? Linear mass density is mass per length. So we can write lambda as mass per length. But length is not given in this problem either. The length of our arc, right, is half of the circumference. A full circumference of a circle is 2 pi r. So our length is pi r. It's half of the circumference of a circle. And now we have written lambda in terms of m and r, which are the variables given in the problem. So we can make this final substitution. 2r squared m over pi r, and don't forget the m that was here. Now we can cancel out some variables, m, r squared, and we're left with 2r over pi. That is the y-coordinate of the center of mass. So if you thought this problem was complicated, yes, it definitely was. I wanted to present it here because we're going to do a lot more of this working in these other coordinate systems when we talk about moments of inertia, and then we're going to do a whole bunch in physics too. So I already wanted to introduce it to you, of starting to get used to change coordinate systems to make it easier to solve a problem.